Okay, here's a Rlc Natural Response, and this is going to be an overdamped. You don't really know that right now, but you're going to find out soon enough that it's overdamped. So it's our same parallel RLC circuit. The only one we're going to solve in Chapter 8, just with different values in here. So there's our, this is a 2 kilo ohm resistor. This is a 250 millihenry inductor. This is a 10 nanofarad cap. There's an initial current IC. There's an initial current IL. There's an initial, or not initial, but well, there's IC, which is a function of time, and IL, which is a function of time, and IR, which is a function of time. Of course, they will have initial values, but specifically the initial values are this capital I sub 0, and that's minus 4 amps. And then V0, capital V0 is 0 volts with this plus minus polarity. So let's see. This is node A at the top, so all the currents, IC, IL, and IR, are shown leaving the node A. Of course, that's impossible. One of these must have a negative value. And, well, this one has a negative value. And partly they're just making it difficult for you with these negative signs. There's a signal of interest out here, V, with polarity plus minus like that. Okay. We're supposed to find what is IR at 0. What is IC at 0? What is V prime at 0? You know, what is the rate of change of this voltage at time equals 0? And then there's this big giveaway that this is an overdamped system because they're asking to find these constants A1. And we have a set of equations for overdamped systems, and they use A's. They use the letter capital A's in them. So that's your sort of clue that it's overdamped right away. But anyway, there's V, and then V of t for t greater than or equal to 0. All of these RLC problems are just greater than or equal to 0 because we don't know, you know, how these guys got like they are. Okay, so the first thing is we need to find the roots so that we we can, even though they're telling you it's overdamped, we can find the roots. So alpha is 1 over 2 RC. We have a formula for that. It's 1 over 200, or I'm sorry, 2K, 10 nanofarad. This can be 25, has units kiloradians per second. So alpha squared is, square that guy, it's going to be 625, and be careful with these. When you're squaring stuff, make sure you get all your zeros in there. It ends up being mega radians squared per second squared. And omega 0, we're going to need that to find our S's, our S1 and S2 roots. So omega 0 squared is 1 over LC. It's 1 over 10 nanofarads times 250 millihenries. It's going to be 400 mega radians squared per second squared. So, you know, right away we've got alpha squared and omega 0 squared, and just by looking at these right now, we can see that alpha squared is greater than omega 0 squared. Alpha squared 625 is bigger than 400. So we know that this thing is overdamped. Okay, now we know that it's overdamped. Before we just had a clue because they had these A values, which is the letter that's used for overdamped equations in the textbook. But now we know that it's overdamped by comparing these two values. Okay, we can calculate the S's. We're gonna need that to. May not be apparent, but we're gonna need that, and we can calculate it. So just do it. If you don't know what else to do, just do what you can, right? So S1 is minus alpha plus root alpha squared minus omega 0 squared. It's going to be minus 2500 plus root 625 times 10 to the 6 quantities squared minus 400 times 10 to the 6 squared. I'm squaring twice here. 625 is alpha squared already, and 400 is omega 0 squared. I have too many squares in here. Yeah, I've got too many squares. Anyway, it's going to be minus 2500. The stuff under the root ends up being 1500, so it's minus 10 kiloradians per second. That's S1. And S2 is the same formula but with a negative sign, so it's going to be minus 2500 minus 1500. So it's going to be minus 40 kiloradians per second. Okay, these are real numbers, right? 10 and 40 are real numbers, and they're different. So this is real and distinct. Therefore, this is overdamped. So this is the second way to know that it's overdamped. So now we're gonna do our tricks. We have several tricks. We have we can use KCL at node A. We can use I equals CV prime, and I've got a couple others that I can't remember right now on my tricks page that are in the notes, but we can find IR right now just by using Ohm's law here. So we know that the voltage across here is at 0 is 0. See this capital V 0 at 0. This capital V sub 0 is 0 volts. So that's the voltage at time 0 is 0. So part A, kind of what we were doing already, didn't seem related to part A, and it kind of isn't directly related. But you have to do this root stuff to figure out what math to use, right? So now we know that we can do overdamped, but now we can actually start to do A. Yeah, we don't actually need overdamped to know right now, but you need to know this stuff eventually, so it's good to just do it up front. But we can find I sub R. So Ohm's law, I equals V over R. So I at 0 is going to be V, at 0 over R. It's going to be 0 over, doesn't matter, it's going to be 0. That's the answer. And part B, we want to know what is the current in the cap at 0. We could sum the three currents. So this is KCL at node A. Okay, so basically I sub L plus I sub C plus I sub R equals 0. They're all leaving, so they're all positive. And we're interested in I sub C right now. So I sub C at 0 is minus I sub L at 0 minus I sub R at 0. And I sub L at 0 is given. It's basically capital I at 0. It's minus 4 amps. So it's negative minus 4 amps, right? We write KCL as all positive terms because IC, IL, and I are all leaving node A. And then solve it for I sub C, so you get these negative signs in here. But then the quantity value you're given for I sub L at 0 is minus 4 amps. Minus I sub R at 0, which we just solved for, which is 0, so it's just 4 amps. That's I sub C at 0. Okay, part C, we want to know what is V prime at 0, and we have this, we have I equals CV prime. We have this current voltage relationship for a cap, and the only unknown there is V prime. So we can solve for V prime. So V prime at 0 is going to be I sub C at 0 over C. And, I sub C of 0 is 4 amps. We just solve for that. And the capacitance is 10 times 10 to the minus 9 farad. It's going to be 4 times 10 to the 8th. Okay, and the units here are volts per second, because it's the rate of change of voltage, right? How many volts are changing every second, so volts per second. That's part C. Okay, part D, so D and E, really, we can sort of solve at the same time. We want to know what these constants A1 and E and A2 are. So we're using the OD EQs because we've previously determined that this thing is overdamped. So you need to determine this stuff at some point so you can know what set of equations to use. So we have these equations. V at 0 is A1 plus A2. And we have this V prime at 0 is A1 S1 plus A2 S2. So these are just from our our toolkit, basically. Our OD toolkit EQs, basically. So, but we've already solved for V at 0. It was given. This is 0. And we just solve for V prime at 0. And we have the roots already. So this S1 is minus 10 and S2 is 40. So this is minus 10,000 A1 and S2 is minus 40,000 A2. And we just solved for V prime at 0. That was 4 times 10 to the 8th. This is 4 times 10 to the 8th. So there's, if you look at this, okay, there's 2 equations, 2 unknowns, right? A1 and A2 unknown, A1 and A2 unknown. 2 equations, 2 unknowns. So there's a solution in there, and skipping the the solving of this simultaneous equation thing, I'll just give you the answers there. 13,333, and A2 is minus 13,333. Those are the A roots. So now we can, part F, we can solve for our voltage as a function of time. So once again, we have our OD toolkit equation. We're given V of t is A1 e to the minus S1 t plus A2 e to the minus S2 t. And we have all of these things. So V of t is 13,333. And just factoring out, the A, and the A is just different by a sign, so you can factor it out and just put the sign in the proper place. It's e to the minus 10,000 t minus e to the minus 40,000 t. volts. So that's this thing. So what is that? So that's the solution. First, determine the damping, right? Then they're sort of walking you through what you need to do, generally speaking, in these things by asking you for these specific things, and that kind of leads up to this thing here. But what does this look like, right? So if you had 13, taking this apart, it would be 13,333 e to the minus 10,000 t minus 13,333 e to the minus 10,000 t. So like this guy's coming down like this, starting at 13,333 and going down at e to the minus 10,000 t. And we can add that to the other. This second term is going to be negative 13,333 and decaying much slower because it's or am I mixing that up? It's decaying faster. I think I might be mixing that up, but anyway, it's minus 40,000 t. I don't want to pause the video and figure that out, but one of these is faster than the other, and so you add these two together, and it's going to well, at 0 it's 13,333 and minus 13,333, so it's 0. And one of these is going away faster, so it kind of pulls it up, right? But then they both decay down to 0, so it looks like this. So to double check the shapes. But anyway, looks like that. Thanks.